Um, didn't talk about like how expected, how like the expected value of each strategy needs to be equal. I don't think, but that's something that at least I feel like I understand pretty well. So it filled in the gaps for me.
When you say expected value, are you talking about like the utility?
Yeah, like if you're going to do a specific what's the terminology they use? Strategy? Yeah. If you're going to use a specific strategy, then the expected value of each support of that strategy needs to be the same. Because if any of them are lower, then you would just remove it and thus get a higher overall expected value.
Exactly.
So like makes sense, perfectly logical, but didn't mention it didn't mention it in the video. But example problems and stuff.
Yeah, did you say go over the example problems? Sorry, my internet cut out.
I did, yes.
Cool. Yeah, let's do it. Do you want me? I can go over. Oh yeah, this is what I was thinking. I can go over the super simple battle of the sexes example. Although have you all seen that video? So we don't need to go over that. That's like the kind of baseline, I think.
I would love to go over it.
Okay, cool. So let me, should I share screen or should I do a?
I mean, if you guys are open to it, are we in agreement that would be useful?
Is that, you mean the video that you linked, like directly in the Battle of Sexes section?
I think so. Yes, that starts the video. I mean, that starts the Nash equilibrium, mixed strategy Nash equilibrium.
I wish I watched this. Yeah, let's go over this because I mistakenly didn't watch this.
Okay, sounds good. So let me do whiteboard. Perfect. So Battle of the Sexes, right? What is the Battle of the Sexes? What are the actual boxes? Do we know? Can someone let me know?
What is it? Hold on a second. Isn't it 21000012?
Yeah. What up, peeps?
What's up?
Hello.
Hey.
So we're going over the Battle of the Sexes thing from that was included in the video that I linked to. But anyway, I've got it down. So what is it? 2100?
Yep.
Okay.
No, not 00 there. Oh no, yeah, 00 there. Yeah, those two corners. Yeah, are both 00.
Okay. Cool. So we've got A, B. So the first thing to notice is while this could be, you could call this like C and D or something. We are going to instead, okay, here, actually, let me formulate the problem first. We are trying to find the Nash equilibrium, the weighting, we're trying to find the weights that we're going to place, how often we're going to play, player one is going to play A, how often player one is going to play B, and how often player two is going to play C, and how often player two is going to play D, right? Does that make sense?
Yep.
Okay, so here, the first thing that we're going to do is instead of calling this C and D, right, we only have two options. So we're just going to instead, let me erase that, and let's just call this, okay, call this P for probability, and 1 minus P. Okay, so that's the first step, just so that we can formulate the problem better. Now, what we're trying to do is we're trying to solve for these probabilities. However, one thing that we know is
Do
that
you guys see the P that's written?
do you see this P?
No,
Yeah.
I don't see anything.
You don't see a P.
This is what I see.
Oh, that's
Oh,
right.
no.
Frozen on CD, but I see P's. I see.
SCPs.
Oh,
P's
it's
in there.
Pass, Andy.
now it's slowly getting drawn. I think I'm like lagging. I think that's what it is.
I
Carry on.
think my internet is so bad in my apartment, and it's really frustrating me. It's horrible.
'Cause now I see the P and the 1 minus P. I see it now. So I think I'm just lagging as hell.
Damn. Okay, well, I'll just continue, I guess.
Just carry on. Yeah, just carry on. Sorry.
Okay, so the utility of A, right, when the other player, or the utility when, I actually don't know exactly why this is the way to formulate it. Like why you would write it like this. But the utility of A, the important thing that I definitely understand is that the utility of A and the utility of B, expected utility of A and expected utility of B need to be equal. Right? And the reason why that is the case is because if the expected utility of A was not equal to the expected utility of B, then we would just play B less or B more, depending on, to equal out those the weights. So if we are in a Nash equilibrium, then we know that the expected utility has to be equal. However, there's a caveat. You don't know that unless you are completely certain that A and B are part of the support of the Nash equilibrium, which means that they are not just irrelevant actions that are not going to be considered ever, that have zero probability of being played. So if they have a positive probability, we know that the expected utility of A must equal the expected utility of B. Does that make sense?
Yep.
Hopefully. Okay. So then we can formulate this whole equation. So we're going to say the expected utility, let's see. So we have P and 1 minus P. So it's going to be 2. Martin, you want to help me formulate this? I'm sorry. I kind of have a general idea, but I'm forgetting the. Let me actually write this out in text.
I think I haven't been following closely enough to help you out here, Carl.
Okay, that's fine. That's fine. I'll figure it out. Why is the text not working?
Welcome to my world.
Okay, whatever. So it's going to be something like, because I feel like we have two variables here, A and B. But it must be wrong. This is it. Okay, sorry. It's 2P. I figured it out. It's going to be 2P plus 0, 1 minus P. Okay, I'm just going to ... It's hard to write. And then equals, right, because that's the top side. So 2P, 0, 1 minus P. And it's going to be 0P equals 0P plus 1, 1 minus P. Okay, so now we can simply figure this out. So that's going to be 2P equals 1 minus P, which then is 3P equals 1 which now we can say P equals 1/3. Ta-da! So now we know that we're going to play P with a probability 1/3 and 2/3 for 1 minus P. Or, D if you wanted to call it that. So, and we can then do kind of the same. Now we can pretty simply figure out we can do the same thing for A and B, where we say, okay, the utility of this one is going to be equal to the utility of that one, expected utility of that one, solve for everything, and then come out with what is actually going to be the same, because these are symmetric. This is a symmetric game. So it will be also, I think it'll be 1/3 for B and 2/3 for A. Okay, so did that make sense?
Did you say that it was going to be symmetric? Because now it's
Yeah.
not. And just to illustrate how much I haven't been following.
So I say that again?
So these probabilities, P, is that player one's state of mind of what player two will do, or
well, yeah. Is this player one up here? I've been calling.
No, the role player is usually player one.
Yeah, this one, right? Yeah. So the probability P is the probability that player two plays action. What could be C or something like that.
Yeah, but I mean, that's what player one thinks that player two will do, right?
No, player two is trying to decide on a strategy.
Yes.
Oh, okay, because also the first element in the matrix, or in a particular input in the matrix, is the role player. So, like when we have 2-1, that would be the first. The 2 corresponds to the role player, i.e., player one. Right?
You mean
Maybe
this
I'm just-
too?
Mm-hmm.
And that corresponds to A, right? Or player one, sorry.
Yeah.
Playing A, yeah. Yeah, that's right. So what is the question or comment?
It was just a clarification and a question at the same time. So you answered it. Thank you.
Okay, cool. Yes. So yeah, the row corresponds to A. I mean, player one. The first number corresponds to player one. And P corresponds to the probability at which we're just this. If you think about this, we're just trying to model out a game, and we have incomplete information about how we're trying to basically take a game that was a pure strategy and move it over to mixed strategy, and then calculate what is the correct Nash equilibrium probabilities for for this game. So what is anyway, does that make sense? Cool.
Thanks for writing it up.
For sure. So I'm going to clear it. Bye. All right. So that is our little, does anyone have I worked on a couple problems and didn't really finish any of them too completely. Does anyone have a preference for something that they would like to either share or talk about? Or should we just do?
I liked 36.2 because we had talked about it already. Or not really talked about it, but discussed it in chat. I posted about it a few minutes ago, but the way that the problem looks here, I guess I'll share. Hold on a sec. So, can you guys see that? Yeah.
Yep.
So, exercise 36.2 says Army A has a single plane with which it can strike one of three possible targets. Army B has one anti-aircraft gun that can be assigned to one of those targets. The value of target K is VK, with V1 being greater than V2, and V2 being greater than V3, and V3 being greater than nothing. Army A can destroy a target only if the target is undefended and A attacks it. Army A wishes to maximize the expected value of the damage, and Army B wishes to minimize it. Formulate the situation as a strictly competitive strategic game and find its mixed strategy Nash equilibria. So in the example from the Less Wrong article that Jared posted, we had two cities, Metropolis and Podunk. Metropolis gave you a payout of 10 and Podunk gave you a payout of 1 if you attacked. So that's how I recognized that it was a similar thing. So basically we want to formulate a strategy that allows you to attack any one of these cities and get the same expected payout. So hold on a sec here. Put up this whiteboard. So if you guessed randomly, then it would be, can you guys see this? Because I was having like problems before.
I see it.
Yep.
Me too.
So if you guessed randomly, it would be 1/3 probability times the value of each target. But, sorry, let me finish this. That's no good for the attacker because the defender would obviously just defend the most valuable one, which is V1, every time, and thus protect the most valuable thing. But then the defender would say, okay, well, if the attacker is obviously going to, the attacker would say, okay, the defender's obviously going to defend the most valuable one, so I'm going to attack the second most valuable one. But then the defender would say, oh, the attacker's going to expect me to defend the most valuable one, so he's probably going to attack the second most valuable one, so I'm going to defend the second most valuable one. And we get into this kooky recursive chain of trying to guess what the other person's thinking and always changing our strategy when we do so. So that's not Nash equilibrium. We want it to be so that nobody needs to change their strategy, right? So the answer was to do a weighted random distribution where you are. Sorry, one sec. The answer was to do a weighted random distribution where all three of these are equal, right? So that would be P. So tell me if I'm wrong here, but because they're all equal, can I just do two of them, like P v1 equals 1 minus P v2, or you have to have all three of them in the equation. I guess you have to. No, they're all equal. So if you want to write this out as an equation with like 3 targets, how would you guys write that out? Where the expected value of all of them is the same. I guess really it's just like.
I mean, isn't it just going to be like you have as a factor v1 plus v2 plus v3 divided by whichever. So the coefficient that you now have as 1/3 in front of v1 would instead be v1 plus v2 plus v3 divided by v1, and the coefficient that you would have in front of v2 would be v1 plus v2 plus v3 divided by v2, and
yeah. That's good. Yeah. So I don't really want to write all that out because it'll take me forever on this stupid whiteboard. But I'll write it out for the first one. So for the first one, the probability with which you want to defend it is the sum of all of them. Divided by the one that you want, in this case, v1. And likewise for the other two. And so like if it was v2 1 and you were dividing by 3, then it would be 2 v1. And so in the case where that's the value of all of our targets, you would defend this one your expected payout. This isn't a probability, is it?
So I just realized that you can set v1 plus v2 plus v3 equal to 1. Because you're right that this is going to be larger than 0, since they're all larger than 0. So it would probably be better. I mean, you want all of the probabilities to be equal, right? So
yeah.
I mean, you get these 3, or you get the condition that you have some constant divided by v1 and some constant, and so on, and you want this constant divided by v1 plus this constant divided by v2 plus this constant divided by v3 to be equal to 1. And from that, you calculate what the constant should be. So sorry about that.
Cool. So if I understood you correctly, then 1 over v1 plus 1 over v2 plus 1 over v3 should equal 1.
It's not necessarily 1.
Sorry, k over 1.
Yeah.
Yeah, okay. And then you calculate the constant that way? Oh, okay. So in the case where it's 3, 2, 1, then it would be yes. Okay. 2 plus k equals 1. And so then let me just do this on paper because I don't really want to do this on the stupid whiteboard.
I love the singing. It's very relaxing.
Agreed.
Who wants to sing? Okay, yeah, continue, please.
So then it's like, oh shit, I did this wrong.
6/11.
I
If
need
you
somebody.
interpret the V3 as a 3, then yeah. But there's some abusive notation going on here.
Yeah.
Okay, cool. 6/11 in this case.
But I think that is the formulation, right? Oh, and
No, this is wrong, guys. Because you're supposed to have k divided by v3 and not k divided by 3.
V3?
oh, no,
Yeah.
because
This was a special case where V1 is 3 and V2 is 2 and V3 is 1.
Yeah, exactly. Yeah, this was with a specific instance that I was trying to do. But anyway, that probably wasn't useful at all.
no, it was actually good. I like, but 6/11 would be that's K, right? So then you would choose, you'd choose V1 6/11 over 3 times.
Yeah.
Yeah.
No, 6/11 over 3 times, exactly. In this case. Okay, so sort of bumbled my way through that. Is it possible to erase all? All right, I can just like stop sharing, can't I?
Yeah, you can clear the screen, but you can also just click the X.
Does that stop sharing?
Yep.
No, don't.
I mean the X on the whiteboard. Oh, there we go. Anyway, well, it did for me, but what else? So is anyone jumping to do a problem? I have something that I did that I can.
I've been sick since we tackled. I've been sick since last time, more or less, so I haven't had time to do anything. So if anyone else has something, just go ahead.
Okay.
Cool.
I Googled a bunch of problems, but I didn't do one myself. I should have. It looks really fun. But go ahead, Carl.
Sweet. I love doing problems. Let me see. I have to open up the. Well, I can share my screen actually already.
Did anyone do the investment one? Or no. Sorry, not the investment one. The guessing right, 36.1.
Right here. Do you want to see my bad attempt? Or shoot.
Oh, no. That one was obvious. I was curious about the investment one. Sorry, I mixed them up. 35.2.
Oh, well, I did. Yep, I did that one too.
Yeah, can you go through that one?
Okay, well, oh boy. First, I just want to appreciate how much easier the notation on Coursera is when compared to our textbook. Like, you first define best response, and then you define Nash equilibrium in relation to the best response function. It's just like very simple, very straightforward. I'm very happy with it. So here is my solution to both 35.1 and 35.2. And we get to see my wonderful handwriting. Whoops, that's really zoomed in. Okay. So 35.1, I just kind of like wrote English, but 35.2, I was very interested in having help. So I'm curious what you guys think about this. So actually, let's go over the problem first. I need to, do I need to do a new share? Let me just share my desktop. Okay, 35.1. Can everyone see 35.1?
Yes.
Very good. So each of n people announces a number in the set 1 through k. A prize of $1 is split equally between all the people whose number is closest to 2/3 of the average number. Whoops, this is point 1, but that's okay. I'll just keep it. Show that the game has a unique mixed strategy Nash equilibrium in which the player's strategy is pure.
This is the beauty contest.
Just a beauty context test. So it's super simple. I think, would you say it's like same logic as the beauty contest, except we know that people aren't going to predict a probability or not going to set a probability, positive probability for anything above 1. By the way, beauty contest, the answer is 1 because everyone races to the bottom, right? So
Why
the
do you race
answer,
to the bottom?
so the reason why they race to the
It's
bottom,
integers. Also, you round to the nearest integer.
So you round down always? No, you can round up too.
Yeah, you just round to the nearest integer.
Okay.
These dollars don't have fractions to like 8 decimal places.
Right. Okay.
yeah. So like essentially all you'd end up doing is, if you didn't choose 2/3 of the average number, then you would want to change your choice, right? You change it to 2/3 of the average, right? And so if everyone is changing to 2/3 and then changing to 2/3 again, changing to 2/3 again, you're just essentially cutting off 1/3 of all the numbers every iteration. And so eventually, even if you start at a million bajillion, then you're like, oh, everyone realizes that their only answer that they can really get is 1, because 1, if you split 1 into 2/3, and it's the lowest number, you can't get any lower because of this constraint, because the set. Does that's like a quick thing, and I think that logic can be extended to just setting probabilities, right? If you set a probability that you would choose 5 with 0.1, and then someone else set their probability that they would choose 4 with 0.1, then you're going to lose because the 2/3, and you're just going to race to the bottom even in your probability. So it ends up one pure strategy choosing 1. Yeah. So hopefully that made some sense.
I think so.
I actually wrote something out.
So, can I ask, would the strategy be different if you were trying to be as close to the average as possible and not 2/3 of the average? Is the reason it's a race to the bottom because it's the 2/3 of the average thing?
Exactly.
So if you were trying to guess if you were closest to the average, would everybody coalesce around like 5? I'm guessing, or something. Or no, sorry, not 5.
Wouldn't every
middle number, like the middle?
no, every number, as long as everybody picks the same number, would be a Nash equilibrium.
Okay.
And if you had it 1.1 times the average, then Nash equilibrium would be infinity.
Okay.
Yeah. Okay.
So I wrote something out. Is basically what I
Actually, yeah. I mean, it depends on how many players there are, or no. Actually, if you have 1.1, then since we have a discrete set where all of the inputs are integers, then you would have the same situation as 1, right? Because you always kind of round it down to the closest integer.
Would you always round it down?
I think you round up, right? You go up.
Yeah, but I mean 1.1. So it depends on what the number is, I guess.
Oh, you mean like if it was 1 1/3, then it would be up to k.
But he's saying if it was 1.1, then you still might be rounding down.
I'm saying that if everybody gets 1, then that's a Nash equilibrium as well, because 1 times 1.1 rounds down to 1, and if you have 2 times 1.1, then that is also rounded down to. So for all the numbers less than 5, those are also Nash equilibria. But I guess k is the closest, so it depends on k in that case.
Wow. True. Cool. So I'll go to 35.2, which is the investment race.
What's the point that in 35.1, when they actually run this, everybody coalesces around the middle, because you're actually trying to guess the average and not 2/3 of the average, and so everybody goes with like the middle number, whatever it is between 1 and k. That's what it like experientially. That's what we see. I don't know. I didn't know if there was like strictly formal reason for that, or if it was just like a function of humans kind of assessing their choices and stuff.
Yeah.
Could you repeat what you said, Andy?
In the cases where there's actually like a beauty contest that people are trying to guess the average or trying to guess what everybody else will guess, everybody guesses who they consider to be an absolute middle of the road candidate. That's what it almost always coalesces on, because that's the only one that they can reasonably assume that everybody else will guess. But like, again, that like adds in a bunch of random human shit, like assuming, like assessing beauty and stuff like that. It doesn't like mean that it's the only Nash equilibria, is what I realized, I guess.
Yeah.
So anyway, let's move on to 35.2.
Cool. And also, I'll link the video that, what's this? I don't know, the class lecture video on this in particular is really interesting, because he does the experiment and you find that people do coalesce around the middle, and then you do it again and people start going lower and lower and lower until it's like ends up at 1. I mean, okay, it doesn't end up in 1 because he doesn't do it enough, but that's what it would end up at. So
I have a really good article too about beauty contests and stuff. It blew my fucking mind, and it'll probably make you a better trader if you ever decide to trade and stuff.
please post.
But Carl, you formulated this in terms of a mixed strategy equilibrium, because I think it's pretty clear that everybody's gonna race to the bottom in the pure strategy one. But can you show your solutions for the strategy case, mixed strategy case?
I didn't actually formulate it very well. I basically made the argument, whether or not it's true, that in the pure strategy case, you race to the bottom, and that if you look at the mixed strategy, like each positive probability that you would place on something that's not 1, you would find that the same like logic applies, where if I place a 0.1 probability on, putting in 5, then if someone places a 0.1 probability on putting in 3, and that's closer to 2/3, then I would then put my 0.1 probability onto, 2 or 1 or whatever it is. It's pretty wimpy. I don't even know if I wrote it out very clearly here.
Okay, and I'm just thinking here, if it's always the case that if you have a pure Nash equilibrium, that you also have a mixed strategy Nash equilibrium. That would be an interesting question.
Yes, it definitely is true, because
What was the thought? Sorry?
If you have a game where there's a pure Nash equilibrium, if the corresponding mixed strategy game also has a equilibrium at that particular point, so a pure strategy.
yeah,
Isn't it certain that it will? Like, are you saying if a game has a pure strategy Nash equilibrium and then you formulate it as a mixed like if you write it in mixed strategy form, but you choose the pure strategy, then will it be a Nash equilibrium? Is that what you're asking?
Yeah.
I imagine that it is like certainly will, because you would really just be like writing a bunch of extra notation, wouldn't you? And then just arriving at the same result. Because
not necessarily, because people could benefit from, like, I'm not saying that this is the case, but potentially people could benefit from like giving some other alternatives some minor probability and thus raise their expected value. So I'm not saying whether this is the case or not, just saying that it could be.
So if you're saying that when you have a pure strategy, that when you formulate it as a mixed strategy Nash equilibrium, that the question is that pure strategy a Nash equilibrium? And the answer, I believe, according to like the stuff that I've seen, is that actually no. And one example of that is I think it is the Battle of the Sexes, or the going to the movies. Yeah, that is Battle of the Sexes, going to the movies. Where in Battle of the Sexes, where what we just saw, we have 2-1, 1-2, right? And 0 here and 0 here, right? 0, 0, of course. And so in a pure strategy, the two Nash equilibrium are this and this, right? And both with played with one probability, and then this one played. It should be like A played with one probability. A time. Oh God, blowing things up. A times 1, and then comma A times 1, or C, I guess, is what I called it before. So this is A, B, C, D. So that's a Nash equilibrium in the pure strategy form. But in the mixed strategy, what we saw is it would instead be 1/3 A, and then we don't know, we're uncertain about that player's movements, and so it'd be like 1/3 C and 2/3 D. And so we'll have cases where we actually don't end up going to the movies with the person in a mixed strategy Nash equilibrium. I don't think I explained that very well, but it does mention this briefly in the video. Anyway, I'm curious what does that make sense? By the way, I apologize if I just went too ham on that question.
I mean, it makes sense because I'm familiar with it, but I'm not sure if your explanation would have helped.
Yeah, exactly. Oh well. Oh my drawing. So the 35.2. Here. Does someone want to see? So in this problem,
Guys, I gotta go a little bit early. Sorry to say. Carl, could you post whatever my assignment is, or what our assignment is, rather?
Well, maybe we should quickly. Why don't we quickly? I don't have to go through this. You can check out the stuff that I wrote up on this. I guess you have to go like right exactly now.
Not like pants on fire right now, but like in a minute.
Okay. Should we? Are you guys interested in going over 35.2, or should we just figure out what we're aiming towards next week?
We can do both. Let's just talk about what we're doing next week right now, really quick, while I'm here, I guess, and then you can just do it when I leave. So I'm guessing we're going to move on to 33.2, right?
Sure.
Yeah, right. Makes sense.
I'm not gonna be able to join next week.
Wait, is next week like a holiday or something? I just want to make sure.
It's the 22nd. So it's like close to Christmas, but not actually Christmas.
You guys want to maybe just like adjourn until after? You want to just adjourn for the rest of 2016, and then just restart like in 2017? Do you think that would be a bad idea or a good idea?
It's fine by me.
Yeah.
I'm fine with either. I will study during the holidays, but I think I'm studying other things too. So
Okay, cool. Maybe, yeah, let's just take our winter break for the semester.
sure.
Okay, cool.
kind of-
So,
We're going to leave cookies now since this is the last day of class.
oh God, I wish I should have brought something for Carl and Martin, definitely.
Yeah, you guys have been really amazing. I was wondering what, like, when we pick up again, you know, there's a lot of pieces of, like, related to game theory, like mechanism design or like social choice theory, and other things. Like, are we just going to kind of continue plowing through this very dense book that we keep needing to supplement, or maybe should we like consider meeting again early in the year around some fresh material?
The one thing I like about the book is that even though it's terribly dense and confusing, it's definitely like a good roadmap through game theory. It's like a bunch of topics that I want to understand well. That's not to say that we shouldn't do other things like social choice theory like afterwards, but I would like to like get all of the topics that are covered in this book well.
I'm into that.
But yeah, I do want to read a social choice theory book next because that's so important.
Yeah, I mean, I think the book is standard in the way that it goes through all of the parts. If we like somebody finds a book that is better and doesn't have all of these annoying notational difficulties that we see in this book, then that would be nice. But I don't know if anybody wants to do some like literature digging over the holiday.
I know of one book that could be, I'll check out one book, but also I think this book actually tracks pretty closely to Coursera. I know I just did Coursera and then I tried to solve the problems in the book with Coursera, and I thought that worked pretty well. So I would suggest, doing something like that potentially.
Okay.
I definitely agree with social choice.
So, okay. So let's plan on re-meeting on the 5th, which is the first Thursday after the New Year's. That's 3 weeks from today, which is a while, but I think it's all right because this isn't urgent. Then the other thing that I was going to say is if anybody, like, I guess, how am I trying to say what I'm saying? If anybody has, like if we decide that we like the Coursera or something like that, let's agree on that at that meeting, and then we can change to, like, do other stuff. But for that meeting, for that January 5th meeting, we should, like, I don't know, like, have something to talk about, right? Should we do section 3.2, I guess?
Yeah, sure. Sounds good.
Is there example problems in section 3.2?
There are a couple.
Pretty decent. Yeah, there's a couple. Okay, that'll be enough for an hour at least. That'll be enough to cover an hour. Definitely. Okay, cool. So let's plan on that. January 5th, we're discussing section 3.2. If people want to, like, bring a proposal to change material at that time, like, you should probably post it in the chat, like, beforehand. Like, I'm definitely going to look at the Coursera shit. And then we will, like, if everybody's in agreement, then we'll, like, like, formally ratify it or whatever, like, at that meeting. Sound good?
Cool.
Awesome.
Perfect.
Sounds good.
All right, team. Have a great holidays. Great rest of the year. So glad that we got this together. I'm so thankful for you guys. I'll see you in a few weeks.
Yeah.
Thank you, Andy, so much. Amazing.
Thanks, guys.
Thank you.
Bye, y'all.
Thank you, everyone.
Hi, Andy.
Bye.